independence of random variables, it's just an extension of independent events and multiplication rule. What does multiplication rule state? For two events A and B. You should know multiplication. So probability of A intersects B is simply equal to the probability of A multiplied by the probability of B. So that's what we have if we have independent events. The concept can simply be extended to random variables. So probability x1 less than or equal to x1, comma, probability of x2 less than or equal to x2 would be equal to that. It's one way of writing it. It's in terms of the CDF. We can also write it in terms of the PMF. We could say probability of x1 equals little x1, x2 equals little x2 is simply equal to probability of x1 equals x1 times probability of x2 equals x2. But both of them are valid. So on the left-hand side, the combined one is what we call a joint PMF. Later on, we will talk about a joint probability distribution function with continuous random variables. So we will just extend this idea to functions, all density functions. So for discrete random variables, the joint PMF, you should be able to write it as a product of the individual PMFs. The comma here indicates intersection. So we don't want to put intersection time and time again, so we'll simply call it as a comma. So if I expand it to n random variables, that would be the joint PDF. Be precise, equals x1, x2 equals x2. What should that equal to?
Probability that x1 equals x1 and probability that x2 equals x2 and so on.
If it doesn't happen, then the random variables are not independent. Good. So that is the joint PMF. Joint PMF is the same as joint probability, A intersects B. You might have had it as joint probability, so this and that are one and the same. Running out of space. Maybe I'll set over here. One more part. So we roll two dice. One is red and the other is blue. Z is a new random variable that is equal to x plus y. X is the outcome of the red die and y is the outcome of the blue die. We want to find the joint PMF of x and y. So what is the joint PMF of x and y? Probability of x times probability of y. Can I write it that way? Yes, no, maybe.
How many sides are on each side?
Regular six-sided die. So Joe tells me that the joint PMF is simply the probability of x times the probability of y. Is that true? Benton, do you say yes?
I would say so.
Why?
They are independent events. The outcome of the first is not dependent on the other, or vice versa.
So probability that x is equal to m, comma y equals n is simply probability of x is equal to m multiplied by probability of y equals n. So m, comma n would be in 1, 2, all the way up to, 6. It's a 6-sided die. Now, does this make sense? If you write all the outcomes out, we know that X would happen in 6 different ways. Y would happen in 6 different ways. In total, they would happen together in 36 different ways. So if I asked you, well, what is the probability that X is 1 and Y is 1, out of those 36 probabilities, it's just 1 out of 36. It's the same as saying the first die resulted in a 1, the second die resulted in a 1. What are the chances that the first die would result in a 1/6 times 1/6, 1/36? Does that make sense? This will work out for all values of m and n. So that's the joint PDF. For all m, n. And if you add every single probability in a joint PMF, it will sum to 1. Just like a single PMF of a random variable, if you have a joint PMF, every single probability when you add must sum to 1. We want to find the PMF of z is equal to some value k. How would we go about doing this? So x plus y is equal to k, and x is equal to k minus y. And where do we go from here? Mind you, that's a random variable, so is that. Unfortunately, I don't have a direct expression for this. In other words, I don't have a formula. All I know is that 1/6 probability. So what is one way of doing this? What are the values of z, the support of z?
2
Huh?
2 12.
Right, 2 all the way up to 12. So k goes from 2 all the way up to 12. What are the possible values for y? 1 through 6, 1, 2, 3, 4, 5, 6, because y is the outcome of the red die, which will only take, the value is 1, 2, 3, 4, 5, 6. I'm going to do it in this way because I want to use it later on. I use There is a reason why I'm doing it this way. We don't have to do it this way. Oh, I use some property here. Can you tell me what that property is? Or a law? the law of total probability. If you recall, the law of total probability says probability of A could be written as a sum of conditional probabilities. So I'm pretty much doing that. If I condition y is equal to n, then that simply means this random variable is no longer a random variable because I conditioned it at n. Does that make sense? So I can rewrite that expression. Can I raise up here? Yes, because I'm conditioning on n, and then multiplied by the probability of y. Correct? Yes, no, maybe. No, I just have to plug in the values. N equals 1, 2, 3, all the way up to 6. But no matter what I plug in, that's going to be constant, correct? So 1 over 6. Just right all the way up to 12. Good. Sure, we can sit around and find a numerical value, but why waste time? Do you understand the process? So you can't simply or directly use the random variable. We have to condition it at a single value to get to that part where we can write z in terms of x. Are we clear? You can plug in the numbers at home. We've done this problem before, right? Sum of x plus y. What about part C? Are x and y independent of each other? Negative, yes. X and y. Negative. What?
Because one dies one, another dies another.
One dies one, another dies another. So the outcome of the red die is not changed. The outcome of the red die is not going to affect the outcome of the blue die. They're just independent of each other. Yes.
The probability of getting both ends to be a specific number is equal to multiplication of the two.
That's a probabilistic argument. So we already showed that probability, the joint PMF can be written in terms of, the individual PMFs of the random variables. Probability x is equal to little x and y equals little y, or mn. Are x and z independent? Why not? Probability of z depends on the probability.
On the value.
So I have seen students take all kinds of approaches to understand the concept of independence. The simplest argument would be z is equal to x plus y, right? Think of it as a function. F of x is equal to something, or y equals something. What do we say? Y depends on x, correct? So if I write z to be equal to x plus y, then z has to depend on x. it also depends on y. Does that make sense? So here, z and x are not independent. How would we show this? Well, probability of z equals k, comma, x equals m. We want the joint PMF. So let's arbitrarily, did I use m or n? It doesn't matter. M would work. We wrote it in terms of, okay. So let's just say k is 8. Good. And m is 20. Are you guys paying attention?
Yeah.
I thought I'd get a response when I said m equals 20.
Oh, yeah. The probability that m is 20 is 0. And x is 20.
It's okay, Chris. Don't take it too seriously. So probability z is equal to 8 and x is equal to 6. It is a joint probability, so I can just throw that in here, correct? Because I already have an expression for that. So 1/6, sum n equals 1 to 6, probability of x is equal to 8 minus 6. Yes? Probability of x is equal to 2, which gives us how much? Right, because probability of x is equal to 2 would be 1/6. We're summing 1/6 to example. I'm thinking a single value. There shouldn't be a sum. Z is equal to k. No. Eight minus n. That's what it should be. So 1/6. When n is 1, I will write it as probability x is equal to 8 minus 1, which is 7. When n is 2, 8 minus 2, we will get 6. N is 3, we will get x equals 5, so dot, 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 all the way up to probability x is equal to what? 2. Good. We know 6 all the way up to, excuse me, probability of x is equal to 6, all the way up to probability of x is equal to 2. They're all equally likely. The probability is 1/6. X is equal to 7 cannot happen. So I'm adding 5 1/6s, so I'll get 5/6. So it is 5/36. Good. Let's see if the individual thing works. So we have
that's the probability that C
so,
equals
yeah,
K and X equals M. But you use probability of Z equals K.
I just wrote it. That is the PMF of Z is equal to 8. So this is the PMF of Z. So I'm evaluating the PMF of Z is equal to 8. Now, can I erase? I'll pick x is equal to m in the sense probability of x equals m. In our case, if m is 6, I want to know the probability that x would be 6. What is the probability that x is 6? 1/6. So I found the probability that z is equal to 8, probability that x is equal to 6. I'm going to multiply them, probability that z is equal to 8 and x is equal to 6 individually. And what would I get? Probability z is equal to 8 is 5/36. Probability that x is equal to 6 is 1/6. I get 5/216. In my excitement to write the right-hand side as x is equal to 8 and m is equal to 6, I messed up this. So whatever we found here is for probability z equals k. Now, what is the probability that z is equal to 8 and m or x is equal to 6? I have x to be 6, fixed value, and I would like to have z to be 8. Yes? So what are the possibilities for that? Y equals 2. So that entire thing would reduce to probability of y equals 2, because that is the only way I am going to get z equals 8 when x is equal to 6. Do we agree? And what is that probability? So that does not equal that. So naturally, z and x are dependent. Yes.
You also have to multiply the 1/6 by the probability that x equals 6. 1/36.
We'll repeat what?
So it doesn't reduce down the probability that y equals 2. You still have to consider x as a random variable. It's not a given.
So there should be probability z is equal to 8 given x is equal to 6 multiplied by probability x is equal to 6. If one is reduced to directly reduced to y. So when we condition x is equal to 6, now probability y equals 2, conditioning x is equal to 6, multiplied by the probability of x equals 6. The probability of y equals 2 is 1/6. Probability of x is equal to 6, 1/6. Still not equal. So z and y are not independent. So I still use the law of total probability, but I used it for one single value. Yes? If you go back and look at the way I conditioned to find z is equal to k, I went through from n equals 1 to 6, but all I'm doing here is I'm conditioning on x is equal to 6 given that x is equal to 6, what are the chances z is equal to 8? So under that conditioning, we will have y equals 2. Should I put that x is equal to 6? Some say, yeah, because the conditioning still should be there, but some say no. I am going to stick with the no part because I am special. So the reason being, the moment you set x is equal to 6, it implies that y equals 2, right? So, and then you multiply by 1/6, you'll get 1/36. Are we clear?
So if you were to ask a question like that in exam, would you want that work?
I'll clearly state, show that they are independent. Good. So we are going to do sum of Bernoulli random variables. And suppose x is equal to y1 plus y2 all the way up to yn. And I'm going to define where y sub k is Bernoulli p. IID, did I mention this before? No. So IID stands for independent and identically distributed. Good. Independent in the sense the outcome here doesn't, affect the outcome of y2 and so forth. Identically distributed simply means every single random variable has the same distribution. In this case, every single one of them has Bernoulli p. Are we clear? So if that is the case, then the random variable x is binomial and it'll be n comma p. I've waited a long time to write this because I couldn't write this earlier when I did Bernoulli and binomial because I didn't mention anything about independence of random variables. Now that we have addressed independence of random variables, if I know that y1, y2, all the way up to yn are independent, identically distributed Bernoulli variables, then x will be binomial, which is the sum of all. Now, does it make sense? How do we define a Bernoulli p-index? We did this earlier. I can wait all day. Bernoulli.
There's two outcomes, so it's a bi outcome. Of success or failure.
Okay.
So, where the probability of one is equal to 1 minus the probability of the other.
Okay. So probability of x is equal to 1 will be p, the success probability, and probability x is equal to 0 will be 1 minus p, that's the failure probability. So we could have only two outcomes. So to understand as to why y1 plus y2 all the way up to yn would be a binomial, give me a simple case for n. And how about 4? N is equal to 4. So suppose n is equal to 4. So how many independent and identical Bernoullis would I need if n is 4? 4. And if I sum, what should I get? X. Right, at whatever value we define for x. So this x is different from that x, so we'll call it xb here. This is the Bernoulli x. So I could have just called it as yi, right? Because that's what these are. Same thing. I could have called it as y from the get-go. Now, I want to get a sum of 4. What other possibilities do I have? X is equal to the sum of the Bernoulli random variables. Typically, we define Bernoulli using the indicator function 0 and 1. So what are the possible values for x? 1 through 4? 0 through 4. Right? 0, 0, 0, 0. And then what else would I have? I need 1, correct? So 1, 0, 0, 0. But that 1, 0, 0, 0 could happen in how many ways? 4 ways. I can write that 4 as 4, choose one position for that 1. So 4 choose 1. So x is equal to x, 0, 1. 4 choose 1 way. And over here, in how many ways could that happen? Exactly 1 way. So that would be 4 choose 0. Good. And I have said that they are independent of each other. So what would the probability be? I'm simply multiplying the failure probabilities of each of them. So 1 minus b times 1 minus b times 1 minus b times 1 minus b. Have 1 minus b raised to 4. Yes. Now put p raised 0 in the middle. So 1 success, right? Bernoulli becomes 1, and 3 failures. So p times 1 minus p times 1 minus p times 1 minus p probability. So p raised 1, 1 minus p cubed. I need to get to I need that to happen. So 2 out of those, 4 Bernoulli variables must result in 1s. So in how many ways could that happen? Another way to write it, you have 4 possibilities. Out of those 4, you pick 2. So 4 choose 2. Success multiplied by success, p squared. 1 minus p, 2 failure probabilities, 1 minus p times 1 minus p, get 2. The next case would be 3. So 3 of the Bernoullis must be 1, so 1, 1, 1, 0. And in how many ways could it happen? I have 4 positions, and then I need 3 successes. So 4 choose 3. P raise 3. Q, 1 minus P raise 1. And the last one is 1, 1, 1, 1. That is the only way to get 4. I could call it as 4 choose 4. 1 minus P raised 0. Does that look like a binomial? If you go through, you can see for each value of x, we had n, which is 4, n, same over there. So n. The other value is just x, 0, 1, 2, 3, and 4. X, p corresponding to the value of x. 1 minus p would simply be n minus x. Good. So the sum of IID Bernoulli random variables is a binomial random variable. Does that make sense?